Thank you for coming. Today, I want to share my recent work, learning reserve prices in second price auctions. This work was done together with Pinyan and Xiao. We will consider the most classic model in auction theory, single item auctions. In this model, the seller has an item to sell, and he is facing n potential bidders. Each bidder I has a private value for this item, and we assume that those values where I are drawn from possibly joint distribution D. In an auction, the bidders need to report their values for the item, and after that, the seller will pick a winner based on the reported values and then determine the winner's payment. To get a better sense, let's take a look at a concrete example of second price auction with anonymous reserve mechanism. Suppose we want to sell artwork by Picasso, and suppose the seller sets a reserve price of $250 million on this artwork. And suppose there are three potential buyers. Alice has a random value drawn from the uniform distribution between 100 million and 400 million, and suppose her outcome value is 200 million. Bob, suppose his value is between also a uniform distribution, and the outcome value is 300 million, and suppose Charlie also a uniform random value, and the outcome value is 400 million. Then let's see how the anonymous reserve mechanism works. First, you say Charlie as the highest bidder will get the item, and his payment is the maximum between the value of Bob and the reserve price. Why? Because you say the auctioneer first use the reserve price to filter the low value bidders. That is, the Alice will be rejected by the reserve price, but both of Bob and Charlie have higher values than the reserve, and so they too run the second price auction, and Charlie as the higher bidder gets the item and pays the value of Bob. So his payment will be $300 million. Consider another example. Suppose the reserve price now is raised to $350 million, and consider the same outcome values of Alice, Bob, and Charlie. Then the artwork again will go to Charlie, and his payment now becomes the reserve price 350 million. Why? Because now Charlie is the only person whose value is higher than the reserve. So he will definitely win, and his payment is exactly the reserve price. So as you can see, a very natural and consider the last concrete example. Suppose the reserve is now $450 million. Then the auctioneer will buy in the artwork, and no bidder between Alice, Bob, and Charlie will get the item. So a natural question for the seller is, well, suppose I know the value distributions of Alice, Bob, and Charlie, then I would like to optimize my reserve price to maximize my expected revenue. And let's consider. It turns out that the second price auction with anonymous reserve is not the revenue optimal auction, and that optimal auction is the well-known Merson's auction. Merson's auction is restricted to independent values, and the optimal revenues are characterized by virtual values. That is, you can say first the seller uses the no value distributions to determine the virtual value functions defined in this way. For every bidder, then using the reported value, the auctioneer will calculate the virtual values of every bidder, and the winner of this auction is exactly the bidder with the highest non-negative virtual value. And the payment of the winner is his or her threshold value for which keep winning. And it's interesting to observe that in the case of IID value distributions, marathon auction degenerates exactly to second price auction with anonymous reserve. But in practice, marathon auction is much more complicated and less used in practice than second price auction with anonymous reserve. Okay, and you say the mentioned models assume that the seller has the foreknowledge of all bidders' value distribution, but in practice, those knowledge is learned from historical transactions or other personal data, and it's a more realistic model would be assumed that the seller just has sample oracle access to the underlying distribution key, and a natural question first started by Cole and Rothgarten in 2014 is the sample complexity of auctions. That is, we are suppose we have IID samples to those to this value distribution key, and our task is to design an algorithm using those samples to obtain an auction, and this auction should generate as a good enough revenue. That is, suppose in the case of marathon auction, our outcome auction A should achieve epsilon approximation to the optimal revenue. That is either a multiplicative guarantee of 1 minus epsilon to the optimal revenue from the actual value distributions, or additive error with respect to the optimal values. That is, in the case of marathon auction, we need to learn almost approximately optimal virtual value functions. And in the case of second price auction with anonymous reserve, since all the designable part of such auctions is just the reserve price, so learning an nearly optimal auction exactly means learning a nearly optimal reserve price. So our task again is to get a multiplicative 1 minus the epsilon approximation to the optimal revenue, or additive revenue loss of epsilon. Okay, and to make this problem interesting, we actually need some assumption on the distributions. Why? Because without any distributional assumption, this problem will be is meaningless. That is, any algorithm has unbounded sample complexity. Instead, 4 canonical distributional assumptions have been made in the literature. First is 0-1 bounded support value distributions, and for this setting, we often consider additive error for revenue maximization. The second setting is that the value distributions are supported on between an interval of between 1 and a very large value of h. For these 2 bounded support settings, we can either consider independent value distributions or correlated values. But notice that only for independent values, Mersenne option revenue optimal. The third and the fourth settings are about regular distributions and MHR distributions. These are two technical assumptions about single-dimensional value distribution. And you say because of this, because regular and MHR are restricted to independent single-dimensional distributions. For in these two settings, we implicitly assume that the value distributions are actually independent. There are hundreds of works on the sample complexity and other aspects of revenue maximization in this topic. Okay, let me give a summary of previous work about the sample complexity of Mersenne option. There is a long line of works studying this problem, and the nearly tight sample complexity was finally settled in the work by Chen Haoguo, Zhi Huang, and Xin Zhang in 2019. In particular, they prove that in the first bounded support setting, the sample complexity is in every setting, the nearly tight sample complexity has almost nearly linear dependence on n, the number of bidders, and a polynomial dependence on epsilon, the approximation error. And in our work, we adopt the technical framework by the work by Guo, Huang, and Zhang to second price auction with anonymous reserve and obtain the nearly tight sample complexity in each of these four settings. It's interesting to notice that this tight sample complexity has no dependence on the number of bidders, and the dependence on epsilon, the approximation error, is exactly the same in every setting as the Mersenne auction. Another interesting thing is that we notice that in the two bounded support settings, our algorithm and our sample complexity results does not require the value distributions to be independent. That is, even for correlated value distributions, the same sample complexity still holds. But for the regular setting and the MHR setting, because the regularity and the MHR distributional assumption each itself assume independent values. So for these two settings, we can our algorithm just work for independent values. Also, I need to mention that our algorithm, in our work, we just prove for the matching upbound. That is, we give algorithm and we prove the matching upbound sample complexity as those results. In contrast, the matching lower bounds are obtained in these two previous works. Okay, next, let me give you a high-level description of our algorithm. First, recall that our algorithm has sample access to the underlying value distribution D, and suppose in total we have m memory samples, and indexed by k from 1 to 3 until n. Our algorithm runs in 3 steps. First, using those samples, we just pick the highest value and the second highest value from each sample, and we use those first order samples and second order samples to construct the empirical first order and the second order CDFs. Next, we use these two empirical CDFs to construct the dominated empirical CDFs. And the important part, the point of this construction is that you see at the two extremes of this CDF, I mean, when the CDF is close to 0 or 1, then we are more careful and we just shrink the empirical distribution by a very small amount. But at the mid part of every CDF, we can be more broad and we can shrink a larger part of the CDF. The intuition of behind these dominated empirical CDFs is that will you say the original empirical CDFs are unbiased estimation of the actual value distribution. So it's an actual first order CDF and the second order CDF. And by shading them by a small amount, with high probability, the dominated empirical CDFs are, again, it's definitely dominated by the empirical distributions. And with high probability, they are also dominated by the underlying actual value distributions. But because we just shade each of them by a very small amount, so the dominated empirical CDFs are very close to the actual CDFs, the actual value distributions. The third step of our algorithm is will we use the dominated empirical CDFs in place instead of the actual value distribution, and we simply return the optimal reserve with respect to the dominated empirical distributions. This algorithmic paradigm is the same as the framework by Guo, Wang, and Zhang in 2019. In particular, this previous work designed such an algorithm for marathon auction, and our main contribution is to show that this framework also works for second price auction with anonymous reserve. I mean, it works not only for individual distributions F1, F2 until Fn as for marathon auction, but actually also works for some sketch of the distribution. I mean, in our case, the first order and the second order CDFs are actually the sketches, some sketches of the actual samples. Another interesting thing is that we show that their framework actually goes beyond the settings of independent value distributions, and we actually, in the two bounded support settings, our sample complexity of our algorithm holds even for correlated value distributions. Okay, then we need to get to analyze how many samples are needed for our algorithm to get a good revenue guarantee. The analysis takes two steps, and the first step relies on the revenue monotonicity property of our option, our anonymous reserve option. Recall that a second price option with anonymous reserve, the outcome has two possibilities. First, suppose there is exactly one bidder whose value is higher than the reserve price. Then in this case, the outcome revenue of our auction is exactly the reserve price. And in the second case, there are at least two or even more bidders whose values all are above the reserve price. Then our auction is exactly the same as the second price auction, and the outcome revenue will be the second highest value. So we can rewrite the random outcome revenue in this formula, and after rearranging, write it in this form. And by taking the expectations, we can rewrite the expected revenue in this formula in terms of first order, the actual first order value distribution and the second order value distribution for every possible reserve R. It's interesting. It's easy to say that you say suppose statistical dominance in terms of value distributions implies revenue monotonicity. I mean, suppose we are given two groups of distributions. The first group is first order and the second order CDFs dominates the second group CDFs. Then the expected revenue from the first group will be higher than the second group revenue. Also, another interesting observation is that the expected revenue it has two terms. The first term just relies on the first order CDF, and the second term just relies on the second order CDF, but not this is exactly the linearity of expectation, and this linearity is exactly the reason why our algorithm can work even for correlated value distributions, because the correlation, even if the value distributions are complicatedly correlated, and the first and the second order CDFs can be correlated in an even more complicated way. But when we talk about expected revenues, there is nothing to do about with such a correlation. The second part of our analysis is will use intermediate object. I mean, the doubly shaded CDF is constructed in the following way. I must emphasize that it relies just it's constructed from the actual value distribution rather than the empirical distribution in the following way. And another point is that unlike the dominated empirical CDFs, which is shaded in this way, we shade the doubly shaded CDF. We shade it by intuitively twice as much. Why we need this construction? Because it greatly simplifies our analysis. You say the actual empirical CDF is unbiased estimation of the actual value distribution, and with high probability, the dominated empirical distribution by shading one unit of distance is dominated by the actual value distributions. But since we shade the double shaded CDFs are constructed from the actual distributions by shading twice as much, with high probability is the empirical distribution is dominated by the actual distributions, but itself dominates the double shaded CDFs. And using this statistic dominance together with the mentioned revenue monotonicity, we can obtain the following tree of equations. And the first inequality simply says that applies this revenue monotonicity. The second inequality simply uses the optimality of our reserve is the optimal reserve with respect to the dominated empirical distribution. So the second inequality simply uses this effect, and the third inequality simply again use revenue dominance. I mean the fact that the shaded empirical distribution dominates the doubly shaded CDFs. And what we need, the only remaining step is to show that even the revenue from doubly shaded CDFs is close enough to the actual revenue. To be precise, first you say by introducing this dominated CDF, it incurs no loss of generality because you say we know that in the worst case, the empirical distribution can be just the double shaded CDFs, and you say we only the amount of our shading scheme is just twice as much as before. And intuitively, you can imagine that this just increases the sample complexity twice and gives the same symptotically the same sample complexity. But this doubly shaded CDF is much more convenient than the empirical distribution to analyze because it's a fixed CDF, but the empirical distributions are random objects that rely on the samples. So our remaining task is to show that even the optimal revenue from this doubly shaded CDF is close enough to the optimal revenue from the underlying actual value distribution. And for this step, we will use a bunch of tools of extreme value theorems and Taylor bonds for regular and MHR distributions. So previously, such tools are developed in the topic called simple versus optimal mechanisms. On that mechanism, the task is to prove approximation ratios of simple mechanism with respect to, in terms of revenue, with respect to optimal revenues. And in our work, we extend such techniques from simple versus optimal mechanisms. I mean, extend such techniques from proving approximation ratios to proving sample complexity bounds of learning algorithms. Consider MHR distributions, for example. By definition, we know that a single-dimensional continuous distribution satisfies the monotone Haskell rate and or MHR in short, satisfies this property if and only if this function G defined based on the value CDF itself is a concave function on the support of this distribution. And using our this concavity, if you are familiar with this topic, you'll know that roughly speaking, MHR properties exactly almost means such a distribution F goes to increase at least as fast as exponential distribution. I mean, in the case of exponential distribution, this function G will exactly a linear function. I mean, that is the boundary case concave function. And it's a fork law that it's a fork law that by scaling this MHR distribution F then such a distribution, I mean, as you can see here, it increase at least at at least as fast as exponential distribution. And our extreme value theorem for such MHR distribution says that not only every individual distribution goes to increase as fast as exponential distribution, but even the first order distribution, I mean the distribution of the highest value of n many MHR random variables, such first order and second order distributions also goes to increase at least as far as exponential distribution. The basic proof idea behind such extreme value distribution is a better geometrical interpretation of MHR distribution. I mean, with a geometrical interpretation of concavity of such distribution GG, and using such interpretations, we will get our extreme value theorems. And for the case of other setting, for the case of other settings, we also develop such techniques, extreme value theorems, and other tools about and tail bounds for regular and MHR distributions. That's all. Thank you.